Better Living Through High Altitude Solar Science. I'm Tonya Hall for ZDNet and Tech Republic, and joining me is Dr. Philip Judge, Senior Scientist in the High Altitude Observatory at the National Center for Atmospheric Research. Welcome, Dr. Judge.
Thank you for having me.
What is the High Altitude Observatory, and what is your role there?
The High Altitude Observatory was started by actually a famous astronomer from Harvard in around 1940, where he sent one of his proteges, Walt Roberts, to look into the effects of the sun on the communications during the Second World War. And the High Altitude Observatory was in Climax, Colorado. And since then, the name was transferred down to the offices, and it's been hosted by University of Colorado. And then later, it was the first division, and Walt Roberts was the first director of the National Center, NCAR, in Boulder, Colorado, which opened around 1960, and it's been there ever since. My role there is scientific leader. There are a few of us in each of the science divisions, and our roles are to mentor young people, help the nation move forward with advice, publish scientific papers, do appropriate research, and that kind of thing, and to reach out.
You and I met in Casper, Wyoming in August of 2017 while we were both there to witness the total solar eclipse. You and your instruments were set up in a peaceful mountain setting, about 8,000 feet elevation, just south of the city. What was your team's research goal for that event?
Yeah, we had a lot of a fairly broad research goal there. In writing these papers that I'm finally getting ready for submission here in 2019, I've discovered that our efforts are really very broad. I had been thinking about an experiment on an airplane a few years before, and we managed to persuade NCAR to partner with one of their airplanes to allow us to use the high altitude aircraft to do that. And a group from Harvard wrote a proposal and flew, but it wasn't complete. We needed supporting observations, and so that's what we did on the ground. And so we fielded an infrared imager, we fielded some white light polarimetric camera, we fielded 4 spectrographs operating from the near ultraviolet up to 5 microns. And these were used in various different modes, as the papers describe.
Back in 1998, you predicted certain infrared wavelengths should be visible in the sun's corona. What did you and your team in 2017 observe? What did they tell you, your observations?
From the ground, we didn't have quite enough sensitivity. The eclipse wasn't quite long enough. We had a lot of thermal background emission. These are brand new instruments. One was developed on the fly by my colleague Jim Hannigan at another science division within NCAR. So we didn't really quite know how sensitive these things would be. But from the aircraft, we did detect some of those lines, and 2 more, which we don't know what they are yet. The aircraft experiment had the advantage of flying along the path of the shadow, chasing it. So it drew out the eclipse from a couple of minutes to 4 or 5, which meant they had more time. They were above the atmosphere. It was clearer, much clearer up there. There was no wobble in the atmosphere motions. They didn't induce motions into the images. And then in the aircraft, we discovered 2 new lines, one of which we believe belongs to iron with 8 electrons removed, which would be very difficult to see from the ground because it lies where water vapor absorbs the radiation. But from the aircraft, it's perfectly clear. And another one, which we just don't know what it is. So in that sense, the aircraft experiment was successful, and we learned a lot from the ground as well, actually, gained a lot of experience.
From a pure research standpoint, how did your observations move spectroscopy forward?
We had never had a spectrum of the outer layers of the sun in the infrared in one go from, say, the ultraviolet all the way to 5 microns in the far infrared or mid-infrared. And we managed to do that and get a spectrum with relatively modest resolution, 20,000 for the ratio of the wavelength divided by the sharpness of the lines that you see or the features you can see. And we did that through the atmosphere. And so we were able to pinpoint precisely where the aircraft lines in emission, which we're interested in the corona to measure magnetism in the corona, lie with respect to the absorption lines in the ground. And this has never been done before. Furthermore, the survey of the entire infrared spectrum towards the very limb of the sun had never been done before. And so we have a series of unique data obtained, within a couple of seconds, 10, 20 seconds from the time when the moon finally covered up the sun. And we can analyze those, and that's what we do in some of these, both of these papers, is to try and look at what we can learn about the structure of the sun's atmosphere as it changes from the simple transfer of heat through radiation towards something else, which forms these things called the chromosphere, the transition region, and the corona, which have been a mystery for the last century or so.
What was the biggest surprise that you found from all of your research?
I think the biggest surprise was the detection of these lines that don't belong. But furthermore, we found by observing all the way through the eclipse with these infrared spectra, we found a very well known line of helium. It's at about 1.08 microns wavelength. It's a very well known line for the sun. But what was amazing was when you block the sun completely and then you look at what's left, we found that that line remained very, very strong all the way through the eclipse. The equivalent lines of hydrogen, however, did not. And that's a real surprise. And that's a puzzle, something which my colleague Jeff Kuhn at the University of Hawaii is very interested in. It may be to do with the formation of neutral helium. The corona is very, very hot. So it's kind of strange that this neutral stuff should be there. And so what Jeff Kuhn is exploring is a long-standing problem involving where is this cool material and what's it doing inside a very, very hot corona. It certainly is not from a prominence. It's not from the chromosphere, because the hydrogen lines show us what that's doing. The helium behaves very differently. So for me, when I looked at those data, I thought, I didn't realize what it was at first. And then I looked at it harder and harder and thought, that line shouldn't be there all this time, but it's still there. And so we think we found something that's been known before, but now it's a little bit better quantified, I think.
For the tech engineers, executives, entrepreneurs, and consumers in our audience, what benefits will they ultimately enjoy from your research?
Oh, well, the real motivation behind this from years ago is to find out if we can measure the magnetism in the corona of the sun. The reason that's so interesting is that the plasma, the gas in the corona, is a byproduct of something else, and that something else is the magnetism. We're all aware of solar flares. We're aware of, some of us are aware of things called coronal mass ejections. These things were known since the 18th century. They could measure magnetic disturbances on the Earth as the sun influences not only with radiation, but also with the expulsion of gas and magnetic fields into the Earth environment. It affects the compasses. The compasses go crazy. We have aurora. We have nowadays, damage to transmission lines. Quebec went out. 30 million people were without power for a few hours in 1989. In 1859, there was a famous event called the Carrington event where, there's a record of a conversation between someone in Boston and someone in Western Canada. And they said, I'm running without any power. And it's much clearer now. We're just running on the auroral magnetic fields changing, the auroral currents. What our research will do is it paves the way towards measuring the changing magnetic fields in the sun. And so it's looking at the origin, the physical origin, what kind of physical configurations lead to the ultimate disruption of power supplies, of satellite communications, the safety of astronauts. So that's ultimately what we're getting. We're away from that yet. And just to add, there's a new instrument, a new facility coming online called the Daniel K. Inouye Solar Telescope. It's this 4-meter class telescope, the biggest one we've ever had for solar physics. And so all this work is building up to that. That's coming online in about a year's time. And we hope to be able to use our results to say, hey, this is what we got to look for. And this is what we better focus on and really measure hard. So I'm excited to see what the young people, probably not me, the youngsters, will get up to with this new instrument.
We can simulate total eclipses with instruments. So why does a natural eclipse, why is a natural eclipse better?
Oh, it's very simple. About 1930, a French genius in the name of Bernard Liot, who tragically died on his way back from an eclipse in Khartoum in 1952, I believe. He successfully achieved his measurements. He developed something called the coronagraph, which is an instrument which makes a fake eclipse inside the telescope. The problem is that the sky is intrinsically bright around the sun, and you have to get rid of all the possible scattered light you can. And with the image motion, so as the sun moves around according to the, if you look along, a road in the summertime, it's very difficult to see a car. It looks like a blurred sort of bubbly mess. That's the same kind of thing we're dealing with all the time. That plus the scattered light. When you block the light outside of our atmosphere before it reaches the atmosphere, you get rid of everything. It's just like having a vacuum in terms of the illumination. The light that comes from the shadow 80 miles or 50 miles away from where you're sitting is so much weaker than the brightness of the corona that you can really see much dimmer things during eclipse than you can with any other technique. Of course, you can go to space, but that's one heck of a lot more expensive.
That's true. The next total solar eclipse in the US will unfold in April 2024, but there is a total eclipse this July in the South Pacific and an annular eclipse in the US in 2023. What plans are you making to attend these events?
Well, I have a daughter that recently got married to a fellow in Chile, and she's living in Valparaiso in Chile, about 3 or 4 hours, maybe 6 or 7 hours south of where the central line of that eclipse is. I'm planning on not doing any observations. I want to go and see it. I've got enough to work on here as it is. So some of my colleagues, however, are going. You spoke to Paul Bryans. I believe he's going down to make some observations following up on our efforts in 2017. I'm going to pay my way and have a good time and have a pisco sour or two under the shadow of the sun.
Well, I tell you what.
In terms of 2024, I may be retired, I may not, but if I'm not retired, I will certainly think if there's something new that we can do. And I have one idea already, which is incorporated in one of our papers of what we should do.
Very good. I tell you what, it was a quite emotional event, and I'm with you. Just observing it is moving enough.
Yeah. Well, I thank you for coming along and for your interest. I certainly enjoyed meeting you. You were great fun, and I hope that you get to see another one and enjoy the wonders of the universe around us in continuing years. So,
well, I'll definitely be there in April of 2024. I wouldn't miss it. Thank you so much, Dr. Philip Judge, Senior Scientist in the High Altitude Observatory, National Center for Atmospheric Research. If somebody wants to connect with you, how can they do that?
I'd say email is best. It's just Judge, my last name, at ucar.edu. I'd be happy to connect with efforts for outreach. I think I'm kind of a fun guy, and I would love to talk to people that have any questions.
Well, and you do a lot of mentoring. So if somebody wants to find out about your mentorship, how can they do that?
Go to our if they're interested in being mentored officially as perhaps a high school student or an undergraduate or even a graduate student. We have programs at NCAR. Look up the National Center for Atmospheric Research and look at the Advanced Study Program. They have various things there, and but just send me a message as well.
Sounds good. Thanks again, Philip. And if you guys want to find more of my interviews, you can do that right here on ZDNet or Tech Republic, or go to my website, tonyahall.net. I've got links to all my social sites. Thanks for watching.